Hey there, it's Shannon, Math Check Myers, and today we'll be looking at mathematical models and least squares analysis. So we're going to also learn a couple of other cool things that you'll need in order to understand this least squares analysis. So let's get started. In this section, we will study inconsistent systems. So we've been doing a lot of study related to consistent systems, but now we'll look at inconsistent systems of linear equations and learn how to find the best possible solution of such a system. So a lot of times, most of the times in the real world, you don't have a model that is perfectly linear, right? People love, improperly using linear analyses on things that aren't linear. So always be careful to look at a picture of your graph to make sure it has a linear trend before you apply any kind of linear regression or this least squares analysis, anything like that to it. All right, so anyway, let's check this out. So if you think about having, some data, and let's suppose that, got a few ordered pairs. Could have something, say, at 1, 1, and then maybe another something at 2, 1.5. So this will be 2, 1.5. This is 1, 1. And then maybe we have something else at maybe 2.5 and 2.5, something like that. Well, what happens is you have some C0 plus C1 times x. So Z0 would be like your y-intercept and C1 would be your slope. And you have this equal to y. So in the case of what we have here, right, these ordered pairs, you have like the first one would be what? All of them will start with C0, and then we'll have 1 times C1 because the x value was 1 in the first order pair, and that's equal to 1. And so that is this one here. And then if you have, suppose, C0, and then the next one would be what? Plus 2C1, and that has an output of 1.5. And that was this ordered pair. And then your third one is C0 plus 2.5. C1 is equal to 2.5. And that corresponds to this third order pair. Groovy? Well, what do we have going on here? I mean, we did something sort of like this before, right? But we wanted to find the polynomial that best fit. Now we are looking for some best fit, so we don't have the actual ordered pairs. But if we take a look at what we have, our coefficient matrix A would be what? Well, we'd have 1, 1 going across, 1, 2, and then 1, 2.5. What would our B matrix be? Good, our B matrix would be 1, 1.5, and 2.5. And our C matrix would be C0 and C1. Groovy? So that's what we're going to be moving towards, and it's very exciting stuff. All right, the least squares problem. Given an m by n matrix A and a vector B in Rm, okay, the least squares problem is to find some x in Rm such that the magnitude of a times x minus the b vector squared is minimized. That's why they call it the least squares problem. All right? Well, in order to move on to that, we have to look at a few different ideas. So let's start with definition of orthogonal subspaces. So the subspaces S1 and S2 of Rn are orthogonal when the dot product V1 dot V2 is equal to 0 for all V1 and S1 and V2 and S2. For purposes of this section, we're going to use the Euclidean inner product for our definitions, just to make it easier. Which is what, aka the dot product, right? For this section. The first example, well, are the following subspaces orthogonal? Well, what should we do? First of all, maybe we ought to take a look at what we have here. So we have two spaces, right? So we could think of this space as the first space and this one as the second space. Good so far? And so looking at our definition, then what needs to be true? Well, we need to evaluate the inner product, dot product of each vector in S1 with the one vector in S2. All right, let's check it out. Well, in space S1, we would have what? The vectors 0, -1, 1, and 1, 0, 0, right? And we want to evaluate the dot product of each of these with the other vector 0, 1, 1, the vector in space S2. So let's see what we get. First one, 0 plus -1 plus 1, we get 0. And then 0 plus 0 plus 0 is 0. So what would we conclude? Good. S1 and S2 are orthogonal. Good so far? All right. Now let's go to the definition of orthogonal complement. If S is a subspace of Rn, then the orthogonal complement of S is the set. So this is the notation for orthogonal complement, kind of an upside down T, is equal to the vector U, which belongs to Rn, such that V dot U is equal to 0 for all vectors V that belong to the space S. Cool, cool? Okay, so what would the orthogonal complement of the 0 vector in Rn be? Well, let's think about this. The definition includes the dot product, right? So here we want to figure out all the possible vectors U that belong to Rn that when multiplied to the 0 vector get a dot product of 0. Good, all of them, right? So in a set format, what would we say? We would just say S orthogonal would be, or the orthogonal complement of S would be U1, U2, all the way down to UN, such that ui belongs to the real numbers for I equal to 1, 2, all the way down to n. Basically all vectors in Rn. All right? What about the orthogonal complement of Rn? Good. Beautiful. It would just be the 0 vector. Cool, cool? All right. So definition of direct sum. Let S1 and S2 be two subspaces of Rn. If each vector x that belongs to Rn can be uniquely written as the sum of a vector S1 from space 1 and a vector S2 from space 2, where x is equal to S1 plus S2, the vectors, then Rn is the direct sum of S1, space S1 and space S2, and you can write Rn equals this direct sum, so it's a plus with a circle around it, means direct sum. Groovy? Okay, so example 2, find the orthogonal complement of S and then find the direct sum of S and the orthogonal complement of S. Okay? So this first space S is equal to the span of this vector. So this would be like our vector S1, and this whole thing would be our space 1 from, if you think about the theorem or the definition above. Okay? Well, let's see what we would have. So for the moment, let's consider the transpose. So S1 transpose would just be 0, 1, negative 1, 1 as a row vector. And we want to figure out, okay, well, what would yield the 0 vector, right, when I multiply this vector to it? So if we let W, I'll say, equal to W1, W2, W3, and W4, and then we evaluate this dot product. So 0, 1, negative 1, 1 dot, W1, W2, W3, and W4, and we want this to equal to 0, right? So what would that give us? We have 0 W1 plus 1 W2 minus 1 W3 plus 1 W4 is equal to 0. Good so far? So then that would just be W2 minus W3 plus W4 is 0. And so here there's going to be, 3 vectors, right? Because we'll be able to parameterize. So if I isolate W2, I'll end up with W3 minus W4. And if we let W3 equal to S and W4 equal to T, what else is going to be happening? Well, we know that W2 would then equal to S minus T. Good so far? And then what? Perfect. You would have W1, you'd have to have span as well. Good so far? We found that W would equal to R, S minus T, S and T, where R, S, and T belong to the real numbers, right? So if we wanted to find a basis, remember how we did all this stuff? W equal to R, S minus T, S and T. Then you'd have what? R times 1, 0, 0, 0 plus S times 0, 1, 1, 0 plus T times 0, negative 1, 0, 1. So you could write here, you could write that the orthogonal complement of S would be equal to the span of these vectors that we found, right? So the span of 1, 0, 0, 0, 0, 1, 1, 0, 0, negative 1, 0, 1. Good so far? So that was one part of it. Find the orthogonal complement. And now what do we need to do? Good. We need to find the direct sum. So what do you think? Good. The direct sum then will be S. So the direct sum of S and the orthogonal complement of S will be R4. Groovy? So let's see. Let's just highlight what each one was. Orthogonal complement of S was this one here. And then direct sum is ended up being R4. Groovy? Okay, next up we have properties of orthogonal subspaces. So let S be a subspace of Rn, then the following properties are true. The dimension of S plus the dimension of the orthogonal complement of S has to equal to n, right? And we saw that there's 3 vectors in a basis for the orthogonal complement. 3 plus 1, right, was equal to 4, R4. Okay, and then Rn is equal to the direct sum of the space S and its orthogonal complement, and then the orthogonal complement of the orthogonal complement is equal to the original space. Now, projection onto a subspace. So we've done the orthogonal projection of one vector onto another. And so now this one here is projection onto a subspace. So if U1, vectors U1, U2, all the way down to UT is an orthonormal basis for the subspace S of Rn, and the vector V belongs to Rn, then it turns out that the projection of this vector V onto this whole space S equals to the vector V dot the vector U1 and then times the vector U1 plus the vector V dot the vector U2 times vector U2, and it keeps going on in that manner until you get to the vector V dot the vector U sub t times the vector U sub t. Cool, cool? So notice that you're going to end up getting a vector out, right? Because each of the dot products will be scalars, and then you will get, and then you'll be multiplying each scalar to a vector. Okay, so find the projection of the vector V onto the subspace S. So S is equal to the span of these vectors here, and V is equal to 1, 1, 1, 1. So if we name these vectors here, if we go with our theorem, well, notice that the ui is up there for this theorem. They represent an orthonormal basis. But if you notice, if you just kind of eyeball the vectors here, they're not all unit vectors, right? So here, let's take a look, okay? S is orthogonal, because if you kind of check all of these vectors, so if we call this vector W1, W2, W3, right? These are mutually orthogonal because they have dot products that are 0 within S, right? So let's find U1. So U1 would equal to W1 divided by the magnitude of W1. So W1 is -1, 2, 0, 0. What's the magnitude of W1? Beautiful. The square root of 5. And so we'll end up getting -1 over root 5, 2 over root 5, 0, and 0. Now what we'll do is, I know this should be transposed, we'll just work with it as a row vector and then transpose it at the end. So now what are we going to have? Beautiful. Do you see that U2 will just equal to W2 and U3 will equal to W3 because both of those are already unit vectors, right? So we'll get the projection of our vector V onto our space S, and that's going to equal to 1, 1, 1, 1, because that's our V, right? So we're following this theorem up here. So V dot U1 times U1. So we'll have -1 over root 5, 2 over root 5, 0, and 0. And then times -1 over root 5, 2 over root 5, 0, and 0. Good so far? Now, what we're going to add to that, plus 1, 1, 1, 1, dot, what was our second vector? 0, 0, 1, 0. And then that will be multiplied to our U2, which is 0, 0, 1, 0. And then we'll also be adding what? Good. 1, 1, 1, 1, dot, 0, 0, 0, 1. And then that scalar will be multiplied to the vector 0, 0, 0, 1. Cool so far? So that will equal to, so our very first one will be, let's see, what is this dot product here? We'll have -1 over root 5 plus 2 over root 5 plus 0 plus 0. So this dot product will be positive 1 over root 5, right? So then when I multiply this together, what's going to happen? Good. My first vector will end up being -1/5 and then 2/5, 0, 0, plus the second dot product is 1, right? And let's do our third dot product will also be 1. So we'll end up just getting those vectors back. So 0, 0, 1, 0 is that second expression. And then we'll have plus 0, 0, 0, 1. So our end result for this, the projection of V onto the subspace S, is what? -1/5, 2/5, 0, nope, 1, 1, and 1. Groovy? Now we have to transpose it. So let's put our final answer over here. We'll get the projection of V onto our space S is -1/5, 2/5, 1, and 1. Groovy? All right. So next up, orthogonal projection and distance. Let S be a subspace of Rn and let the vector V belong to Rn. Then, for all vectors U and S, where U is not equal to the projection of V onto S, it turns out that the magnitude of V minus the projection of V onto the subspace S, which remember is the distance between those two vectors, has to be less than the magnitude of V minus U, which is the distance between V and U. Okay, so far? Okay. So, if you look at it kind of like this, so if you have some space, you've got this space S, okay? So this is our space S. And then you've got some vector V. So let's say that you've got this vector V. Well, the projection of the orthogonal projection of the vector V onto the space S is going to look something like this. Okay, so let's say that we've got this set up right here. All right, if you look at drawing a perpendicular down, right, to make a right angle here, this happens to be the vector V minus the projection of the vector V onto the space S. Let's make this bigger. Okay, so far? And so what the theorem is saying here is that if you've got some other vector U, all right, some other vector U, and it starts like here, right? Let's say it starts here and continues out a bit. So that's our vector U. What this theorem is saying is that this distance here between V and U, so this is the magnitude of V minus U, which is the distance between V and U, that's always going to be greater than V minus the projection of V onto the space S. Okay? So this distance is always greater than this distance. Cool, cool? All right. So, next up, let's talk about fundamental subspaces of a matrix. Recall that if A is an m by n matrix, then the column space of A is a subspace of what? Beautiful, Rm, consisting of all vectors in the form A times X, where X belongs to Rm. The four fundamental subspaces of the matrix A are defined as follows. So remember that this here denotes the null space of A, column space of A, and we're focusing in this case of, null space and column space of A and A transpose only. The null space of A transpose, column space of A transpose. All right? So here we go. Let's find bases for the 4 fundamental subspaces of the matrix. So for A equal to this matrix here, let's find our reduced row echelon form. RREF of A was equal to 1, 0, 2, 0, 1, negative 1, and what? 0, 0, 0. And then the reduced row echelon form of A transpose, we got okay, so the column space of A is going to be, so what I did here is I went ahead and just found the reduced row echelon form of A and A transpose. So I'm going to use pivots. So do you see that the pivots for A are in the first 2 columns? So we'd have column 1, column 2, and column 3, and we'll use those first 2 columns. So R would equal to, we'll just write this as the span of our basis, our A basis, and that is what? We use the columns in the original matrix A, and we'll get 0, 1, 1, and we'll get negative 1, 2, and 1. Cool so far? All right, very good. The column space of A transpose would be our R of A transpose. And so that would be what? Good. We'd have the span of, well, where's the pivots? The pivots in RREF A transpose are again in the first 2 columns. And so, sorry, I didn't write out A transpose, but A transpose would have been equal to 0, 1, 1, negative 1, 2, 1, and then 1, 0, 1. Cool so far? So when I look at the pivots for A transpose, look at the pivots in the reduced row echelon form of A transpose, it means I need to again use the first 2 columns of A transpose. So that will give me, beautiful, 0, negative 1, 1, and 1, 2, and 0. So I found 2 of the fundamental subspaces. So the null space of A and null space for A transpose is what? So just so we have track, this is column space of A, column space of A transpose, and then now we're working on the null spaces. So remember, for null space, what do we have to do? You have to solve what equation? Well, we already found what the reduced row echelon formats of each, right? And so what do we have? You could have 1, 0, 2, so I'm using RREFA, 0, 1, negative 1, times x1, x2, and x3 is equal to 0, 0, 0. We want to find all 3 by 1 vectors that'll yield a result of the 0 vector. Cool, cool? So what do we end up getting? Well, we end up getting x1 plus 2x3 is 0. And then we get x2 minus x3 is 0. So x1 would equal to negative 2x3, and x2 would equal to x3, right? So what we get for this one is we get x equals x1, x2, and x3. And if I let x3 equal to t, what would happen? So I'm finding a basis for x. So we would get, well, x1 is negative 2x3, so that'd be like negative 2t, right? x2 equals x3, so we get t and then t. So if we factor out a t, we're going to get negative 2, 1, 1, right? So n of A is equal to the span for our basis, which is the span of negative 2, 1, 1. Groovy? So this one here yields our null space of A. And then we're now working on the null space for A transpose. So our REF A transpose was 1, 0, 1, 0, 1, 1. So 1, 0, 1, 0, 1, 1 times x1, x2, x3 equal to 0, 0, 0. Well, what does that yield? We'll get x1 plus x3 is equal to 0. And then x2 plus x3 is 0. So we'll get x1 equals negative x3, and again we'll name x3t. And then we'll have x2 equals negative x3 equals negative t. So our x will be x1, x2, x3, which is negative t, and t, which would be t times negative 1, 1. So the null space for A transpose is going to equal to the span of negative 1, and 1. That's in a set. Groovy? And that is our work for our null space of A transpose. And those are the four fundamental subspaces of A. Okay, so all right, so now fundamental subspaces. If A is an m by n matrix, then the column space of A and the null space of A transpose are orthogonal subspaces of Rm. And then the column space of A transpose and the null space of A are orthogonal subspaces of Rn. And you end up with what? Beautiful. R of A, the direct sum of R of A and N of A transpose would equal to Rm. And the direct sum of R of A transpose and the null space of A will equal to Rn. So now we get to our least squares problem, finally. So here in this visual here, we've got, so this vector here, right here, is going to be we'll just call this the vector B. We want to get it in terms of our letters, okay? And then we've got this vector here is going to be A times X, which is equal to the projection of the vector B onto the space S. And then now this other distance here, because we've made this orthogonal, so this distance right here, so this distance here, it's a vector, is actually B minus the projection of B onto S. Cool? And as you can see, it's orthogonal. So, here we go. Coming back to the least squares problem. Recall that we are attempting to find a vector x that minimizes the magnitude of A times x minus B, where A is an m by n matrix and B is a vector in Rm. Let S be the column space of A. So S equal to R of A. Assume that B is not in S, because otherwise the system would be what? Good, consistent. And we're looking at that inconsistent system. We are looking for a vector A times X that's in S that is as close as possible to B. This desired vector is the projection of the vector B onto our space S. So A times X equal to the projection of the vector B onto the space S, and A times X minus B equal to the projection of B onto S minus B is orthogonal to S equal to the column space of A. However, this implies that A times X equal to B, or minus B, is in the column space of the orthogonal complement of A, which equals the null space of A transpose. So AX minus B is in the null space of A transpose. The solution of, and you can see this, what this yields this following kind of equation. So A transpose times A times X minus B would equal to the zero vector, right? For that to be true, A transpose times AX minus A transpose times B would equal to the zero vector. But what would that imply? That would imply that A transpose times A times X would equal to A transpose times B. Cool? The solution of the least squares problem comes down to solving that n by n linear system of equations, A transpose times A times X equal to A transpose times B. These equations are called the normal equations of the least squares problem, A times X equal to B. All right? So, example 5, find the least squares solution of the system A times X equals B. So we have A, we have B, we need A transpose. So what is A transpose? Good, we'll have 1, negative 1, 1 going down, and then 1, 1, 1, 0, 1, 1, and 1, 0, 1. Cool so far? So we need to solve A transpose times A times X equal to A transpose times B. Cool so far? So let's check it out. What was our A transpose? 1, 1, 0, 1, negative 1, 1, 1, 0, and then 1, 1, 1, 1, times A, and so that's 1, 1, 0, 1 going down, negative 1, 1, 1, 0, and then all ones, and then times, so this A transpose is 3 by 4, right? And A is 4 by 3. So do you see that we'll get a 3 by 3, which means that X must be 3 by 1. Cool so far? Well, this is going to equal to what? A transpose times B. So 1, 1, 0, 1 going across, negative 1, 1, 1, 0, and then 1, 1, 1, 1, and B is 2, 1, 0, 2. Cool so far? And you can look at the dimensions. This here is a 3 by 4, and this is a 4 by 1, so we're going to get out a 3 by 1, which is appropriate. All right, so I'll let you do the multiplication on those. It turns out that you get so then what do we want to do to solve this? We want to find the augmented, the RREF form, the reduced row echelon form of the augmented matrix, 3, 0, 3, 5, 0, 3, 1, negative 1, and 3, 1, 4, 5. And that ends up being 1, 0, 0, 7, 6, 0, 1, 0, negative a half, and 0, 0, 1, 1 half. So, what does that tell us? That tells us x1 equals 7, 6, x2 equals negative a half, x3 equals positive a half, and so our vector x equals 7, 6, negative a half, 1 half, and we're done. All right, let's look at an application now. The table shows the numbers of doctoral degrees Y in thousands awarded in the U.S. from 2005 to 2008. Find the least squares regression line for the data, then use the model to predict the number of degrees awarded in 2015. Let T represent the year with T equal to 5 corresponding to 2005. All right? So this is from the United States National Center for Education Statistics. So here we go. This would mean that T is 5, T is 6, T is 7, and T is 8. All right? So let's take a look and make sure we've got a linear trend. So I'm going to go to Stat, Edit, and I am going to put my inputs, my T values in list 1, and then my Y values in list 2. So we have 5, 6, 7, 8. And then list 2, we will have 52.6, 56.1, 60.6, and 63.7. All right. So then what you do is you quit out of there, and you want to go to second y equals to turn on our stat plot, list 2. Done. Cool, cool. So if we hit enter, done. Graph. All right, so we need to get to our data. Remember, we need our y scale to be... All right, so as you can see, we do have a linear trend. So as you can see, we do have a linear trend. I'll actually plot these in a different color. These are our points. And so we have a linear trend, so we're good. And this is our t-axis, and this is our y-axis. All right? So let's check it out. What do we need to do? We need to find or solve the equation A transpose times A times C, in this case, is equal to A transpose times B. All right? Well, remember we were working with C0 plus C1 times T was equal to Y, right? So, kind of putting all that together, let's check it out. We would end up having 1 C0 plus 5T is equal to what? Good, 52.6. And then 1 C0 plus 6T was equal to 56.1. 1 C0 plus 7T is 60.6. And then 1 C0 plus 8T is 63.7. Cool so far? So we checked that we had a linear trend. Linear trend, yes, check, right? And then now we have the means to make our A, right? So our A equals the coefficient matrix 1, 5, 1, 6, 1, 7, and 1, 8. Good so far? B equals 52.5, 56.1, 60.6, and then 63.7. All right? And then A transpose will be 1, 5, going down, 1, 6, 1, 7, and 1, 8. And C is equal to C0 and C1. Groovy? Okay, so let's do it. A transpose times A times C is our left side. So we'll have and that's got to equal to A transpose times B. So I'll have 1, 1, 1, 1, 5, 6, 7, 8. And our B was 52.5, 56.1, 60.6, and 63.7. Right? Okay, so when you do all the computation, what you get is, for these two, you're going to have 4, 26, 26, 175. And notice that's symmetric. And then that's times C0, C1. And that's got to equal to 233, I'll just write 0.00, and then 1533.40. And it turns out that we would find the, reduced row echelon form of this augmented matrix. And the reduced row echelon form for that turns out to be 33.68 and 3.78. Okay? And so this gives us that C0 is 33.68 and C1 is 3.78. So what we found is that our prediction model, okay, and usually, in statistics, you want to put like a hat above your, to show it's a predicting model. So our prediction model, call it y hat at t, is going to be equal to what? C0, which was 33.68, and then plus 3.78 times t. And if we evaluate y hat at 15, because that was the second question, right, for 2015, then we end up getting, turns out we get 90.38. So if this linear trend continues, let's answer the question. We predict that 90,380 doctoral students will be awarded doctoral degrees, degrees will be awarded in 2015. Groovy? All right, so here's one result, and then here is another result that we were looking for. All right, so there we have it. That's the least squares analysis. All right. Next up, we'll be looking at eigenvalues and eigenvectors and diagonalizing matrix. So stay tuned, and hey, if you like what I'm doing, please subscribe and tell your friends. Bye.